Welcome back to the deep dive. Today, we are doing something a little different. It's an intellectual exercise, really, a journey into computational extremity.
That's a good way to put it.
We're not talking about optimizing Python or scaling a neural network or, the latest JavaScript framework. We are doing the opposite. We are stripping computation down to its absolute bare bones theoretical atoms.
That's right. And our source material for this is, it's pretty special. It comes directly from a rigorous university course on computability and complexity. We're going to be analyzing a theoretical language. It's called MiniPy.
MiniPy.
Right. And it basically serves as a proof of concept for minimal computation.
Right.
So our mission for you, the listener, is to really try and grasp the ingenuity that's hidden in this extreme minimalism, to see how functions we all rely on every day, things like logic, recursion, even string manipulation, can be built from, well, almost nothing.
It's funny because if the whole goal of modern programming is abstraction and convenience, MiniPy is the deliberate, almost painful opposite.
It is. This language has been intentionally gutted.
Gutted is the right word. I was looking through the source material, and it feels less capable than a pocket calculator from, the 1970s?
Oh, easily. So before we even touch the code solutions, I think we have to define the constraints. We have to lay out the rules of this game.
Okay, let's do it. What are the rules?
The rules are absolute,
Uh-huh.
and they are severe. First, we are dealing only with natural numbers.
So 0 and positive integers. That's it.
That's it. No negative numbers are allowed, ever. And our entire computational toolkit, it's reduced to just 3 fundamental operations.
Three operations to build everything. Okay, what are they?
First, symbol increment.x plus equals 1.
Yeah.
You can add 1 to a number.
Yeah, I can count on it.
Second, decrement.x narrows 1. But, and this is a huge point, it's not standard subtraction. It's what's called saturating subtraction.
Saturating, what does that mean?
It means if the variable x is already 0 and you try to decrement it, it just stays 0. It can't become negative.
Right.
The number line stops at 0.
Ah, okay. That's a crucial constraint. So there's no way to sneak in negative numbers as temporary values or for indexing or anything like that. The floor is 0.
The floor is 0, absolutely. And the third and final building block. The only control flow structure we have is the while loop.
That's it.
That is it.
That is genuinely astonishing. So let me just recap. For me and for everyone listening, I have increment, I have saturating decrement, and I have a while loop.
Yep.
And that means no strings, no lists or arrays, no booleans, no true or false.
No true functions with a call stack. No recursion in the traditional sense.
And crucially, no built-in multiplication, no division, no modulo.
Exactly. It is pure, raw arithmetic manipulation guided by one single flow structure. And our entire task in this deep dive is to interpret the theoretical genius that allows complex modern computing concepts to emerge from just these 3 atoms.
Okay, so let's unpack this. The big theoretical question that the source material poses is this. How is it even possible that a language that has been intentionally stripped of all modern convenience, a language that is so mathematically constrained, how is it proven to be Turing complete?
And that's the million-dollar question. It feels impossible, but it's the bedrock of computer science.
It really does. So where do we even begin to answer that?
Well, what's truly fascinating here is how this language, it really grounds the very definition of computability. The theoretical proof, it relies on this concept of sufficiency, which, goes all the way back to Church and Turing.
The Church-Turing thesis.
Exactly. The idea that these few building blocks, our increment, our saturating decrement, and the while loop, are in fact theoretically sufficient to simulate every computable function.
So you're saying that if I can write a program in Python or C++ or Lisp, but no matter how complex, there's a theoretical equivalent program in MiniPy.
Yes. It might be impossibly long and tedious to write, but it exists.
That's a huge claim.
It is. The way to think about it is we're just transforming a deterministic initial state. The source material calls it the start state, into a final state, the end state. Your variables start with certain numbers, the program runs, and if it finishes, they end with a new set of values. The program is just a pure deterministic transformation machine.
Okay, but we have to address the elephant in the theoretical room right away. We're relying solely on the while loop for control. That means we have no mechanism, no way to guarantee that a program will ever stop running.
That's right. And that's not a bug, it's a feature of the theory. MiniPy programs can very easily enter what the source material calls infinite loops. The original German term is Endlosschleifen,
Love that word.
and this is where the theoretical framework brings in the concept of partial functions.
Okay, walk us through that distinction. Why partial?
Well, think about it. If you give a program an input and it runs forever, it never actually produces an output, right?
Right, it just computes forever.
So for that specific input, the value of the function is simply undefined. A partial function is one that is defined for some inputs, but not necessarily for all of them.
So when we say MiniPy is Turing complete, what we really mean is that it can calculate the set of partial computable functions. The programs don't have to halt for every single input you could possibly imagine.
Exactly. They only have to halt for the inputs where the function is defined and the program is written correctly to terminate. For everything else, it's allowed to run forever.
That is such a crucial distinction. It separates the domain of the theoretically possible from the domain of, like, the practically guaranteed if you don't define your input correctly or your logic is flawed.
The program just vanishes into the theoretical void of infinity.
Wow, okay. So that philosophical framework sets the stage for, well, for dealing with all the stuff that's missing.
It does. So let's tackle the most common sense objection. The one that immediately springs to mind for any modern programmer, which is, but without strings, I can't do anything useful. How do you deal with text?
Right. This is where it gets really interesting for me, because the language of computation, when you get right down to it, it isn't text, it's math.
And the course material offers one of the most elegant, most powerful conceptual leaps in computer science history. It traces its lineage all the way back to Gödel numbering. And the answer is it's so simple. Strings are just numbers.
So you map them, you create a system.
You map complex structures, like a sequence of characters, onto the infinite set of natural numbers.
So if I have a tiny alphabet, say A, B, C, D, I could assign them numerical values, like
Yep.
A is 0, B is 1, C is 2, D is 3.
Yeah.
Then a string like B a D becomes a number that's encoded in a base 4 system.
Precisely. Let's say we use 1, 2, 3, 4 to avoid issues with leading zeros. So if A1, B2, D4. The string BD becomes a number. Let's see, $1 bill for 42 plus 2 kudo 41 plus 4.
16 plus 8 plus 4, 32. The string BD is the number 32.
It's just one single gigantic natural number that holds the entire sequence. And that has a profound implication for computability theory. It's this. The actual representation, whether you see bad D as text on your screen, or you see its corresponding number 32 stored in a single variable, is completely irrelevant to the power of the language.
As long as you can manipulate the number correctly.
If you can manipulate the large number arithmetically, you can perfectly simulate manipulating the string logically. The theoretical power of MiniPy doesn't change just because it lacks a string data type.
Okay, this forces us to think differently. We're using the single natural number variable space, not just for counting, but for structured data storage, all encoded mathematically.
Yes. And that means all the operations we take for granted, reversing that string, checking for a substring, replacing a character, all of those must be accomplished purely through arithmetic on that one big number.
You're moving all the complexity from the data structure itself into the algorithms that manipulate it.
Every single high-level operation immediately devolves into a set of incredibly detailed, low-level arithmetic steps. And you have to realize that to understand any of the solutions we're about to look at.
Okay, so we've established we can represent complex data. But our next huge hurdle is control flow. We need basic logic. We need A and D or R IF statements. But we've only got numbers and a while loop.
So we have to start with a convention. Since there's no Boolean type, we have to rely on number values to represent truth.
Right, this feels familiar from other languages.
The convention is rigid. The number 0 is false.
Yeah.
Any number that is not 0, so 1 or greater, is true.
Simple enough.
However, this is the first major implementation challenge that the source material points out. Just having a non-zero value for true isn't good enough for doing arithmetic-based logic.
Why not? If I just want to test a condition while x is not 0, that works fine for a simple true-false test, right?
It works for testing, yes, but not for calculating. Imagine you have two true inputs. One is stored as the number 5, and the other is stored as the number 10, and you want to calculate the logical AND of those two. The result should be true.
Which we'd want to represent as another non-zero number.
Exactly. But what if later you want to use a formula, like for XOR? That requires clean, predictable inputs. If you try to multiply your 5 and your 10, you get 50. Sure, 50 is true, but it's not a standardized true. It's useless for subsequent formulaic logic that expects a clean 0, 1.
I see. So you're saying we need a process to guarantee that any non-zero value, no matter if it's 1 or 5 million, gets squashed down to a clean standardized 1.
Yes, we have to normalize it. This normalization step is mandatory before you can perform clean Boolean arithmetic.
Okay, so how do we do that? How do you turn, say, a to v5 into x1 without using an if statement or a greater than sign or any comparison operators?
We leverage the same core trick that we're going to see over and over, a self-terminating loop structure. This is the heart of what the source material calls the guardian loop.
All right, walk me through this normalization. I have a variable x, which is 5. I want a new variable, let's call it x norm, to become 1.
Okay. You'll also need a temporary variable, let's call it t. First, you copy the value of x into t. We'll get to how copy works later.
Yeah.
For now, just assume we can do it. So t is now 5.
Got it. X norm is 0, t is 5.
Now, you set up a loop while n is not 0.
Okay, the loop will run because 5 is not 0.
Inside that loop, you do two things. First, you increment x norm by 1, so x norm becomes 1.
Yay.
Second, you immediately terminate the loop. And you do that by setting t to 0. The easiest way is t.
Ah, so you use the value of t to destroy t. Since t was 5, t of 5 makes it 0. The loop condition is now false.
Exactly. So if x was 5, t becomes 5. The loop runs exactly once. X norm becomes 1, t becomes 0, the loop exits. And if x was 0 to begin with,
Then t would be 0, and the while loop would never even run, so x norm would just stay at its initial value of 0.
perfect. You've just created a normalization macro. The result, x norm, is now guaranteed to be either 0 or 1. And this preparatory step, it just reveals the first layer of meticulous manual programming that MiniPy demands for everything.
Okay, so now we have our normalized zeros and ones. We can finally simulate the universal decision primitive, the if statement. And this is done with the guardian loop trick.
This is the centerpiece of all control flow simulation. So imagine we've calculated our condition, maybe it's A and E or RC, and we've stored the normalized result 0 or 1 in a variable called, say, B.
The structure looks so simple, it's just, well, b is not 0. That's our entry point to the conditional block.
The genius is the immediate termination instruction.
Yeah.
The very first action inside that loop body, before you do any of the code you actually want to execute, must be to terminate the loop itself.
So just like in the normalization, the first line is BEB.
Exactly. It uses its own control value to consume itself.
Let me trace that out loud. If my condition was true, b is initially 1. The loop condition while b is not 0 is met. Program enters the body. The very first line sets b to 0. Then the rest of my code inside the block executes. At the end, the loop checks the condition again, sees that b is now 0, and terminates.
And the result.
The code ran exactly once.
And conversely, if b was initially 0, what happens?
The condition while b is not 0 is immediately false. The entire block of code is skipped.
And there you have it. You've simulated a perfect, non-repeating if branch.
Purely through a single self-terminating while loop. I have to admit, seeing that reduction, that an if statement is fundamentally just a controlled block of code that runs at most once, that is the ultimate aha moment. It shows that the control flow is just. It's entirely wrapped up in the state of a single number.
And any complex decision, like the if, x, and y, or z we mentioned, it's just a matter of pre-calculating that logical formula step by step into a single normalized variable b, and then wrapping your execution block in that guardian loop. This trick is foundational. Every single jump, every conditional assignment has to use this pattern.
Wait, I have a common sense objection here. If every logical decision needs a guardian loop, and that loop needs a normalized variable, and normalization itself requires copying variables and another loop, the resulting MiniPy program for something totally trivial, like if x is greater than 5, set y to 10, must be, I don't know, dozens, hundreds of lines long.
It is. It absolutely is. And that complexity is necessary because you are forcing all of that high-level logic down to the absolute primitives. The source material confirms it. The length and tedium of the code grows exponentially compared to high-level languages.
But that complexity is the proof.
That's it. The goal isn't efficiency. It's never about efficiency. The goal is sufficiency. We are proving that this minimal machine can do it, even if the implementation is, well, incredibly tedious.
That distinction, sufficiency versus efficiency, that feels like the real takeaway from this section. We can build logic, but at great cost.
A very great cost. And that cost gets even higher when we move from simple logic to something like recursion.
Right. So the guardian loop solved our control flow problem. But now we face recursion. And traditional recursive functions, calculating the sum of numbers or the Fibonacci sequence, they rely entirely on a function call stack.
A stack to remember the state, the local variables, the return location of each nested call.
And MiniPy has no functions, no call stack. So what does that mean for us?
It means we have to replace that stack-based, self-referential process with pure iteration and very explicit state management. We, the programmers, have to take over the job of memory and state tracking entirely inside the body of a single while loop.
Okay, let's start with a simple example from the material, summation. It's in Präsenzsaufgabe 2. We want to calculate the sum of all numbers up to $.
Conceptually, it's very simple. You use an accumulator variable, call it result, you start it at 0. Now you have a loop that counts n down to 0, and in each step, you add the current value of no $, to the result.
Simple in concept, but, as the course material warns, devastating in implementation because of this thing you call variable juggling.
Exactly. First, we need to formalize how addition even works in MiniPy. We don't have a plus operator. So the addition macro, let's call it add, x, y, has to be implemented as a loop.
How?
It's a loop that decrements y until it hits 0, and for every single time it decrements y, it increments x. So it's like pouring the value from y into x, one drop at a time.
So the statement result plus n is actually a whole loop. While n is not 0, result plus 1, n equals 1.
Precisely. And what's the most important consequence of that?
Oof. The addition macro is destructive. The source variable, n, is 0 when you're done.
It's completely consumed. And that's a huge problem if you need the original value of n to control the main summation loop, the outer loop that's supposed to be counting down from, say, 10 to 0.
So if I start with n10, and my first step is to add 10 to my result, I can't use n directly in that addition macro because n would immediately become 0 after that first sum, and my main loop would terminate instantly. I'd get a result of 10 instead of 55.
This is the core of the juggling act. You must preserve the value of n for the main loop's condition, while simultaneously using a copy of n for the destructive addition operation. And the solution is the mandatory constant use of temporary variables. The source often denotes them as t.
So before I can even add, I have to copy. But hold on, how do you even copy a variable from a to b if the fundamental operations are destructive? A simple loop would destroy a to create b.
You've hit on another layer of the complexity. A non-destructive copy operation, copy A, B, must itself be implemented with great care. It requires a third variable, a temporary one, t.
So 3 variables just to copy one number.
The least. Here's how it works. First, you pour the value from A into t. That's the destructive loop. Well, LA is not 0, t plus 1, a minus 1. At the end of this, A is 0, but t holds the original value.
Okay, so I've moved the value. Now I need to get it back into A and also into B.
Right, so now you run a second loop, this time driven by t, while t is not 0, 1, b plus 1, b plus 1.
Ah, I see. You use T to simultaneously refill A back to its original value and fill B with that same value. It's like pouring water from bucket A into bucket T and then using T to fill both A and B back up.
That's the perfect metaphor. So if you want to add n to result while preserving n in your summation program, the sequence becomes 1. Declare a temporary variable t. 2. Run that non-destructive copy nt macro, which itself probably uses another internal temp variable. Now n is preserved and t holds the value we're allowed to destroy.
3. Run add result t. This loop consumes t but correctly increases result. And 4, I can finally do my main loop's decrement, n at E1, on the original preserved n.
Every single operation that reads a variable must first ensure it has an untainted copy to work with. The programmer is manually managing memory allocation and deallocation at the most granular level imaginable.
The cognitive load must be immense. You're constantly thinking about which variables are safe and which are about to be destroyed.
It is. Now let's up the ante. Let's look at the Fibonacci sequence from Hausaufgabe 1. This is even harder because it requires tracking 2 previous states.
Right, the recursive definition is fibn-1 plus fibn2.
To simulate this iteratively, we need a disciplined little state machine. We'll track 2 consecutive Fibonacci numbers using, say, a variable a for the current one and b for the next one.
So in each step of our main loop, we need to calculate the new next number, which is a plus b. Then we have to shift the old b into a and shift our new sum into the new b.
And here's the problem. We have to execute those steps sequentially. We can't do what you do in a high-level language, like Python's a, b equal b, a plus b. That's a parallel assignment.
Yeah.
He uses the old values of a and b for the whole calculation simultaneously.
And MiniPy forces sequence. So if I just try to do it step by step, I'm going to run into trouble. If I write, say, a equals b as my first step,
Right.
and then my second step is b, a plus b,
Yeah.
well, I'm using the new value of a from step 1. I've just calculated b plus b, which is completely wrong. I needed the original value of a.
Exactly. You just destroyed your state. So the implementation requires meticulous planning and even more temporary variables. You need at least one to store the original A, one for the original B, and one to hold the resulting sum before you start moving things around.
So the real sequence with all the juggling has to be something like, first, calculate the new sum, sum temp equals A plus B, and that add macro itself requires copies of A and B to make sure the originals survive the calculation.
Step one. What's next?
Then I can update A. So I do a non-destructive copy from B into A. So now A has the value that B used to have.
Good. So now A is correct for the next iteration.
And finally, I update B by copying my sum temp into B. And then after all that, I have to clean up and reset all my juggling variables for the next loop.
Yes. What looks like a single elegant line of code in Python translates into dozens, maybe even 100 lines of mini-Py code, all dedicated purely to preserving and moving numbers between these temporary storage buckets.
And the source material stresses that the key to proving that this mess is actually correct is something called the loop invariant.
Yes, this is a core concept in formal verification. The programmer has to be able to formally prove that at the end of every single step of that complex loop, no matter how many temporary variables are used and destroyed, the variables A and B will always contain exactly 2 consecutive Fibonacci numbers.
The difficulty of writing the code is directly tied to the rigor you need to maintain that invariant manually. You don't have a compiler or a runtime stack to help you. You are the stack.
You're the stack, and that's the ultimate confirmation of what recursion really is. It's just iteration with extremely disciplined manual state management.
Wow. Okay, we've built logic, we've simulated recursion. Now we move to, well, arguably the most abstract concept in the entire course material, string manipulation. This is from Presence of Gob 3 and House of Gob 2.
Yes.
We have to figure out how to reverse a string or replace characters when that string is just a single giant natural number encoded in base N.
This is where that base encoding principle becomes an operational reality. To keep it simple, let's just stick with base 4. That means our alphabet has 4 characters, which we'll represent with the digits 0, 1, 2, and 3. And our string is just one large number where each digit's place value corresponds to a position in the string.
The aha moment here has to be realizing that every single string operation we think of, reading a character, removing a character, adding a character, must correspond perfectly to an arithmetic operation on that one number.
Exactly. But to do that, we first need to build some more tools. We have to figure out how to implement the high-level arithmetic operations that are missing from MiniPy's atomic set.
Right. We still don't have multiplication, division, or modulo.
And for this section, division and modulo are the most critical.
So let's walk through that. How do you implement division? How do you calculate, say, A divided by B using just increment, decrement, and while?
You do it with repeated saturating subtraction. To calculate AB for integer division, you start a counter variable, call it Q for quotient, at 0. Then you enter a while loop that needs to run as long as A is greater than or equal to B.
But wait, we don't have a greater than or equal to comparison operator. How do you structure that loop condition?
We have to build that comparison too.
Yeah.
We use the saturating property of our decrement to check if A equal B. You can calculate a temporary difference, T equals AB. If A really is greater than or equal to B, then T will be some number greater than or equal to 0. But if A is less than B, T will try to go negative and it will saturate at 0 now.
But then you can't tell the difference between AB0 and AB0.
Ah, good catch. The actual check is a bit more clever. You can check if BA saturates at 0. If BA is 0, it means B was less than or equal to A. It's a bit of reverse logic. So inside our main division loop, we repeatedly perform that complex subtraction macro, which itself is a destructive loop. And for each successful subtraction, we increment our quotient Q.
And the remainder, the result of the modulo operation. That's just the value that's left over in A when the loop finally terminates because A has become smaller than B.
Exactly. The entire division operation is a giant nested structure of destructive loops and temporary variables. But this primitive is what finally enables us to perform string manipulation.
Okay, so with division and modulo now established as these complex, low-level macros we can call, let's get back to the string reversal algorithm. We need 2 basic string operations. Pop and shift.
Pop, which means reading the last character of our string number. Since we're in base 4, the last character is simply the digit in the lowest place value. Mathematically, that's the number modulo 4. So we run our big division by 4 macro, but we ignore the quotient and just take the remainder.
And shift, which means removing the last character. In our number system, that means shifting all the digits one place to the right. Mathematically, that's integer division by the base. So we run the division by 4 macro again, but this time we take the quotient and throw away the remainder.
And with those 2 tools, we can now dismantle our old string number, piece by piece. The reversal algorithm involves building a new number, call it new string, at the same time as we're dismantling the old string. We pop a character from old string, and then we push it onto the new string.
Okay, let's break down that push operation. How do you add a new character, a new digit, to the front of the reverse string that you're building?
Well, to make space for the new digit in the ones place, we first have to shift all the existing digits of new string one place to the left. And how do you do that in a base system?
You multiply by the base. We have to multiply new string by 4.
Which brings us to the multiplication primitive. We don't have a operator. So how is xy implemented?
It has to be repeated addition.
Repeated addition. To calculate x4, for example, you start a result variable r at 0. You can use a constant counter, c4. And you run a loop. While c is not 0, add a to r, x preserved, c limit of 1. And of course, that add macro is destructive, so you need to be adding a preserved copy of x each time.
Unbelievable. Okay, so the push operation for our string reversal requires 1, running the multiplication primitive, which is itself a loop of addition, so r equals new string 4. And 2, you then add the single-digit character that you popped off the old string to r.
Yes. You're using multiplication to handle the place shifting, and then a simple addition to append the new digit. So string reversal, which in our minds is this elegant algorithm of arrays and pointers, becomes in MiniPy a continuous loop of modulo, which is a subtraction loop, division, another subtraction loop, multiplication and addition loop, and addition, yet another subtraction loop.
All operating on these potentially massive natural numbers, and every single one of those loops requires meticulous variable juggling to not destroy its own inputs.
It's an incredible nested Russian doll of computational complexity.
Mm-hmm.
And the source material reinforces the critical warning here over and over, the dangers of aliasing. Because every single one of these macros, modulo, division, addition, is destructive to its source variable. You must always work on copies. If you use your main old string variable in the macro that implements division, you'll destroy the string number before you've even finished the first step of dismantling it.
The programmer has to think so many steps ahead to ensure data integrity. I can't imagine debugging this. It must be absolutely ferocious.
It is. But this section solidifies that philosophical point we made earlier. String manipulation in MiniPy is nothing more than pure arithmetic acting on large, encoded numerical representations.
It's just math all the way down.
All the way down. So for our final section, let's look at the purest theoretical challenge from the problem sets. It's from Halfaf-Gabe 3, calculating the exclusive OR, or XR, of two variables, x and y.
Okay, so this is a core operation in digital logic. It's used everywhere, from encryption to graphics, and we have to calculate it without any native bitwise operators.
We have to return to the premise that if x and y are properly normalized, meaning we've already run our macro to guarantee they are either 0 or 1, then there must be some pure mathematical formula that perfectly describes the XOR operation.
And what is it?
The source material provides this just beautiful algebraic reduction. X or y is equal to x plus y 2xy.
Wow. X plus y 2xy. It's so elegant. Let's walk through the 4 possible cases to confirm this works. We have to assume our inputs are normalized to 0 or 1.
Okay, case 1, 0 XOR 0. The formula gives us 0 plus 0 to 0, which simplifies perfectly to 0.
Correct. Case 2, 1 XOR 0. We get 1 plus 0 to 1, 0. The multiplication term is 0, so it simplifies to 1.
Right.
The same works for 0 XOR 1.
The formula gives us 1 plus 1, 2, 1, 1. That's 2, 2, which is 0. It works. The formula is mathematically sound for binary logic.
This simple arithmetic definition is so powerful. It proves that XOR, this high-level digital logic gate, is entirely reducible to just addition, subtraction, and multiplication. But now, the implementation hurdles in MiniPy start all over again.
Of course. First, as we said, the absolute necessity of the normalization step. We have to run that whole macro we discussed at the beginning to ensure x and y are clean zeros or ones. That process alone takes many lines of code.
Second, we have to simulate that multiplication term, 2 by y. Since we don't have an operator, this is achieved through repeated addition, just like we did in the string reversal section.
It's immensely taxing. To calculate x, y, you need a loop that runs y times, and inside that loop, you run the destructive addition macro, which is itself a loop. And then you have to double the result, which means adding it to itself, which requires even more loops and variable juggling.
So we're dealing with deeply nested while loops just to calculate one term in our formula.
Deeply nested. And finally, you have the subtraction, x plus y, 2 base y. And because we only have natural numbers, what property of our subtraction becomes critical here?
the saturating subtraction. Because if for some reason our calculation was flawed and x plus y ended up being less than 2 by y, the result would try to be negative. But in MiniPy, that's forbidden. The subtraction macro will just halt at 0.
That reliance on the inherent saturating decrement property is key to ensuring the final result stays valid as a natural number.
What stands out here is just how complex the implementation is for such a theoretically simple formula. The elegance of x plus y 2xy is completely overshadowed by the sheer computational misery required to calculate it using only our 3 primitives.
And that confirms the core philosophical lesson of the entire source material. Logic is, in the end, also just arithmetic. All high-level complexity, whether it's decision-making or data manipulation, is ultimately grounded in the structured movement and manipulation of counts. The only difference between a simple counter and the most sophisticated XOR function is the sheer length and complexity of the nested while loops you need to manage the arithmetic.
And the programmer is forced to manage every single primitive step, line by painstaking line.
Every single one.
So let's try and bring all of this together. We started with just 3 atomic operations: increment, saturating decrement, and the while loop. And we have, I think, successfully demonstrated how the source material proves that these primitives are sufficient for universal computation.
We really have. We simulated conditional IF statements using that self-terminating guardian loop, which ensures a code block runs at most once. We managed complex recursive state machines like Fibonacci by explicitly juggling variables, creating copies to prevent aliasing, and maintaining these strict sequential updates to honor the loop invariant.
And we manipulated abstract data structures like strings, all by encoding them as large numbers. We treated operations like reversal as pure modulo and division arithmetic, which themselves had to be implemented via these deep nested subtraction loops.
It is a profound, if, as you said earlier, painful demonstration of theoretical power. And the source material's conclusion is emphatic about this. Programming in MiniPy is undeniably tedious.
Musam, as the original text says. Tedious, laborious.
The cognitive load required to manage every variable copy, to prevent aliasing, to implement fundamental operators like multiplication from raw incrementation, it's immense.
But the very difficulty is the whole point.
It is. The lack of abstraction forces this profound insight into the absolute atoms of computation. We aren't just using tools, we're proving that the tools themselves are sufficient to build the entire theoretical space of computing. It reminds us that every application, from a basic calculator to the most advanced AI, fundamentally boils down to moving numerical values around in a meticulously defined sequence.
The elegance of those solutions, though, especially the arithmetic reductions for logic, that remains the most surprising takeaway for me.
Indeed.
Yeah.
We broke down the arithmetic definition of XOR as x plus y 2xy, and that should leave you, the listener, with a final provocative thought to mull over, a way to synthesize everything we just discussed about primitive implementation. We saw how tedious it was to build multiplication and division. So if x plus y 2x high is a definition of XOR, what simple arithmetic formula represents the most basic logical operation of all, the NOT operation? And once you have that formula, how many lines of pure increment, decrement, and while loops would it take to actually implement that tiny foundational piece of logic?
Just to flip a 1 to a 0 and a 0 to a 1.
Just for that, the sheer scale of that implementation challenge. That is the true heart of minimal computing.
A fantastic and frankly a slightly terrifying note to end on. Thank you for diving deep with us into the atomic structure of computation. We will see you next time on The Deep Dive.